Okay, so in this video I'm going to be talking about oxidation states or oxidation numbers. So and as you can see, there's a bit of stuff already on this periodic table. This stuff is from my electronegativity. Sorry, my voice is sounds strange. Anyway, so you can see all this stuff. This is from my electronegativity video, and before I go on to explain these oxidation numbers and oxidation states, if you haven't seen your electronegativity video, I suggest you go and see it, because electronegativity is one of the underlying fundamental concepts behind oxidation states. So yeah. So oxidation numbers. Now oxidation numbers is something which basically what it's referring to is the most likely ion that something will be if it was an ion. So you can imagine if something is bonded to, say, let's imagine an element bonded to itself. What do we breathe in that helps us to live? Oxygen. So I'm going to start with oxygen. Oh, let me just adjust my pen size. I'm going to start with oxygen. So imagine we had two atoms of oxygen. Obviously oxygen is like O2, so it looks like this, like when it's bonded. So we have two atoms of oxygen here, and they're bonded together with two electron, like a double bonded together basically. And so using the idea of oxidation states, meaning that if both of these atoms were ions, what ions would they be? So if we take a look at this, well, not ions, but if they were to be split up, what charge would they have? And that's basically what oxidation states mean. Oxidation numbers and oxidation states means. And if we were to split up two oxygen atoms, they're both equally greedy for when it comes to electrons. So they're probably gonna split the electrons 50-50, the ones that they're sharing. So if you can imagine these electrons, these 4 electrons that they're sharing are gonna be split. So oxygen is going to take 2, oxygen is going to take 2, and before they split, they had a new overall charge of 0. The overall charge was 0. So after they have split, their overall charge is also going to be 0 because they've split their electrons evenly. And so after they've split, and we've got the oxygen here on its own with 6 electrons, it's still going to have a charge of 0. And because of the fact that it still has a charge of 0, we say that the oxidation number of oxygen when it's bonded to oxygen, or sometimes we refer to it as combined oxygen. No, not combined, uncombined oxygen, as in oxygen bonded to itself. We say that uncombined oxygen has an oxidation state of 0, and this is why, because if we were to split it up, it would have a charge of 0, and you can imagine this would be we would have the same sort of thing for the other atom here. And so, but if we had, say, 2 different elements on this periodic table, and which weren't the same atom, didn't have the same sort of greediness for electrons, the electrons probably won't be evenly distributed. So let's say we had oxygen and hydrogen. So maybe we had H2O. So oxygen bonded to hydrogen, bonded to hydrogen. In fact, what I'll do is I'll draw it in a form which, so that you can see the shared electrons. And I'll draw oxygen in red, so because when you get one of those molecular kits, you usually get oxygen as red. So I'll draw oxygen as red. So this is oxygen, and this would be bonded to hydrogen through 2 covalent bonds. So we'd have a covalent bond here. So you can imagine the gray is the electrons of hydrogen, and the red is the electrons of oxygen. So as you can see here, there's 2 electrons being shared. Let me just draw on a hydrogen. There we go. So we've got the hydrogen here, and we'd have a hydrogen here as well. It's a bit big. What just happened? Alright, I'll switch to white pen by accident. We have another hydrogen here, and this would basically have the same sort of bonding. So we'd have two electrons shared, and oxygen has 2 lone pairs of electrons. And this basically means that those 2 electrons aren't bonded to anything. They're just sitting there on the oxygen. And so in this bond, right, if we go back and look at the periodic table, and if we look at it from the perspective of electronegativity, we can see that hydrogen compared to oxygen, as I said, electronegativity increases as you go this way in my last video. And again, if you haven't seen it, please go and watch it so that you can really understand this. And as you go along, the electronegativity increases. Well, yeah, electronegativity increases. So hydrogen is going to be less electronegative, and oxygen is going to be more electronegative. More electronegativity, less electronegative. And so oxygen is going to have more of a force exerted on these this shared pair of electrons, and so it's going to be pulling these electrons closer toward it, whereas hydrogen is going to be pulling with a force, but it's not going to be as strong as the force of oxygen. And so if we were to split this, right, oxygen is probably going to double cross hydrogen and steal its electrons. So if we were to break this bond, oxygen is probably going to take these electrons. Since we're imagining that this is an ion now, just for the purpose of looking at oxidation states. And okay, let's look at the electrons which oxygen had before. Oxygen before had 1, 2, 3, 4, 5, 6 electrons, and this was before the whole bonding and everything. No more oxygen. And we've added 2 more electrons, and we've imagined that this has become an ion, and it's stolen these 2 grey electrons. Well, they're not really grey, but we've taken these 2 grey electrons which were from the hydrogen, and we've given it to oxygen. And so oxygen now has, imagining that we've made it an ion now, oxygen would now have most likely have an oxidation state of 2-, because it's got a charge. Oxygen will have a charge of 2-, and oxidation states are basically the charge, and so it would have an oxidation number of 2-, or oxidation state. It's basically the same thing, oxidation state, oxidation number, and it would be 2-. Whereas hydrogen, since it's basically been double crossed by oxygen and it's lost its electron, it's going to have a charge of +1. So but it's not too bitter about that, because it doesn't really care about these electrons that much. It didn't exert as much of a force on it, obviously, because of the lack of the nuclear charge, nuclear force of attraction. And so yeah, so the first rule we can come up with here is that combined oxygen has an oxidation state of 0, which you can basically deduce from the periodic table, and hydrogen has this being combined with oxygen has an oxidation state of +1. And this isn't always the case, but since oxygen is so much more electronegative than hydrogen, this is the case here. But as I said before, if you go down the group, electronegativity decreases even further. So if we were to bond, say, hydrogen with anything with a lower electronegativity than hydrogen, which is basically everything in this column, I won't go into like the stuff in that column, but everything in this column has a lower electronegativity than hydrogen. If we were to bond it with any of these things, hydrogen would have an oxidation state not of +1. So, because if you imagine hydrogen is here and the thing it's bonded to is here, so maybe Li, or any of those, hydrogen would have a oxidation state of -1, because if you were to split this, and let me make this clearer to you. These two electrons have come from the two different atoms. If we were to split this, hydrogen is most likely going to take both electrons and leave lithium without electrons, because hydrogen in this case has the upper hand. It's got a stronger force exerted on the electrons. And lithium, on the other hand, as you can see, it's got a greater nuclear radius, and so the force is not as strong, and so lithium is left without the electron. And so if you take away an electron from lithium, it's going to have a charge of +1. It's still got electrons, but it's got less electrons than protons, so it's going to have a charge of +1. And so we say that even though it's bonded, we imagine that it's got a charge, it's got an oxidation number of +1. Because when we look at it from the perspective of oxidation numbers and oxidation states, we picture that all of these elements or atoms that are bonded are ionically bonded. Because in ionic bonds, we have the charge, so we have Na+, maybe Na+ and Cl-. We have the charges there written explicitly. Whereas in covalent bonds, we usually don't have a charge written there. But from the electronegativity concept, we can figure out that charge from the periodic table. So yeah. Now, some other tricky sort of exceptions which we might discover are OF2. OF2, like, well, actually, you just looking at periodic table, you can see fluorine is more to this side, oxygen is more to that side. So obviously, fluorine is going to be more electronegative than oxygen, even though usually oxygen nearly always has an oxidation number of 2-. Fluorine here is more electronegative, so it's going to double cross oxygen. So if we had oxygen, and let's say instead of hydrogen here we had 2 fluorine, so we had OF, what's going to happen is oxygen is not going to take the electrons. Fluorine is going to take the electrons, leaving oxygen with an oxidation state of 2+. And fluorine would each have a charge or an oxidation number and charge of 1-, -1. So in this particular case, due to the increased greater electronegativity, fluorine is going to have an oxidation number of -1. So that's one of the sort of, you could see it as an exception. We say exception because there's few elements with a higher oxidation or higher electronegativity than oxygen. I know chlorine is sort of close to fluorine, but chlorine, I remember asking one of my chemistry teachers, what has a more, which of these elements is more electronegative, oxygen or chlorine? And my teacher was like, I don't know. But yeah, I've done a little bit of research, and well, oxygen is more electronegative. And yeah, so if we had oxygen bonding to chlorine, so OCl2 maybe, oxygen would still have an oxidation state of 2-. It wouldn't be 2+ like it isn't with oxygen or fluorine. So OF2 is in fact like practically the only exception, unless oxygen is bonded to itself and bonded to something else, in which case it turns slightly different. If oxygen is bonded to itself and something else, so let's say because oxygen has a valency of 2, that means it can bond to 2 atoms at a time. Maybe it could be bonded to itself and bonded to something else. So in this case, what I'm going to draw is hydrogen peroxide, and the hydrogen peroxide has the formula H2O2. So we have the hydrogens and we have oxygens bonded to each other. So first of all, let's look at this bond. In this bond, what would be the oxidation numbers of oxygen and oxygen? Obviously, oxygen is not going to be greedy with electrons when it's sharing it with oxygen, so the oxidation number is going to be 0 in this particular area. Now, if we take a look at this area, oxygen doesn't really think hydrogen has what it takes to keep the electrons very close to it. So oxygen is going to be kind of greedy in that area, and also this oxygen is pretty much the same. It's going to be greedy in that area. So over here, oxygen is going to have an oxidation state of -1, and over here oxygen is going to have an oxidation state of -1. So in total, both oxygens combined have an oxidation number of -2. But if we say what is the oxidation number of oxygen, we're gonna have to, since there's two oxygen atoms, we're gonna have to divide this -2 by 2, and that gives us -1. So we say that in this particular molecule, oxygen has an oxidation number of -1, or oxidation state of -1, and hydrogen has its usual oxidation number, which is +1. So yeah, that's what it would be in that case. And if you think about complex molecules, like complex ions, not complex ions, but let's say a molecule like OH. If you remember from alkalis often produce OH minus ions when in solution, and OH minus isn't just one atom. It's a two atoms bonded together, and it's an ion overall. Now, what would be the oxidation state if we said, what is the oxidation state of this hydroxide ion? This is the hydroxide ion. What is the oxidation state of the ion? Now, if we're asked that, what we do is we just look at this charge, which is, as you can see, 1-, and we'd say that the oxidation number of this ion is 1-. It's just the overall charge, so it's a very similar concept. And so let's say we had, let's go to the other side. So hydrogen bonds to maybe in a sulfuric acid we've got H2SO4. Hydrogen bonds to this sulfate part of the acid, and if we were maybe trying to figure out what the oxidation, let me draw that 4 a bit smaller, it looks a bit dodgy. 4. So if we were to try to find out the oxidation number of this area, the general rules apply. Like these two H plus H, if we imagine them to be H plus ions, and this is overall neutral, this would presumably have an oxidation state of 2-, since it has to balance out the 2+, which is over here. And so if we were asked to find the oxidation number of SO4 2-, or SO4, it would be 2-. So yeah, that's basically the idea of oxidation numbers. If you want to find more, there's a lot of information on the internet about this. So yeah.